Okay, so this video is going to be over kinematics 1C, which has to do with motion graphs. In the last video, we talked about acceleration and solving problems with constant acceleration equations. And so motion graphs, basically, the two types of motion graphs we're going to be looking at are position time graphs and velocity time graphs. And motion graphs basically give us another way to solve problems with kinematics and with motion. And so a lot of the concepts are going to carry over to this section. So, as always, please follow along closely, take notes, ask questions if you need any help. The first thing we're going to look at is the two types of motion graphs, like I said, the position time graph and the velocity time graph. And basically what these graphs are is they're ways of describing how an object is moving over time. Okay, and so we're going to start off by looking at the position time graph, and then after we do some examples with that, we'll look at the velocity time graph. You do need to be able to interpret these graphs and understand the motion that they're describing, and you also need to be able to find the slopes of the graphs in order to solve some problems. Okay, so hopefully you recall how to find the slope of a graph from your algebra class. So the first thing we're going to look at is what's called a position time graph. Now, the symbol for position is x, and so sometimes you'll see these labeled as xt graphs. Basically, what a position time graph shows you is how the position of an object changes over time. So, for example, let's take a look at our favorite simulation, which is the moving man. Okay, so I'm going to move this guy back and forth, and this is a position time graph. And what you'll see is as I move him back and forth, okay, the blue graph represents his position. So at the beginning, he was at this position 0 meters. Okay, as I move him to the right, his position increases. Okay, so now his position is 6 meters. If I just hold him there, you can see his position doesn't change. As I move him backwards, notice his position goes back down towards 0. And if I move him in the negative direction, his position becomes negative. Okay, and so to understand what this graph is saying, you can basically think of the y-axis, the position axis, as basically being like a number line, and you can imagine an object like the moving man moving back and forth along that number line. And then on the x-axis we have time. Okay, so that's basically what a position time graph is. Now, a few things to look at when you're analyzing a position time graph. The first thing is going to be the y-intercept of the graph. The y-intercept of the position time graph tells you where the object starts their journey. In other words, the initial position of the object. So for example, let me reset this moving man. Okay, so let's say I give my moving man a velocity of 1 meter per second, and I give him an initial position of, let's say, 2 meters. Okay, so that means when I hit play, he's going to start moving, and he's already at the 2 meter mark. Okay, because I gave him a velocity of positive 1 meter per second, he's going to move with a velocity of 1 meter per second in the positive direction to the right. Okay, so when I hit play, take a look at this graph, and you can see on this graph, the y-intercept on this graph, you can't actually see the number, but the y-intercept on the graph right here represents the initial position of the moving man. Okay, so that's that 2 meters we're talking about. So on a position time graph, the y-intercept tells you the starting position of the object. Now, more important than the starting position is the velocity of the object. So you can actually look at a graph of position versus time and actually find out what the velocity of the object is. And the reason you can do that is because velocity is basically the rate of change of an object's position. Okay, now in algebra you should have learned that rate of change on a graph looks like slope. So in other words, here's the key piece of information you need to know to solve problems. On a position time graph, the slope of the position time graph tells you the velocity of that object. Okay, in other words, how fast is it moving? So when I go back to look at my moving man, he's moving with a velocity of 1 meter per second because that's what I said before. And so the slope of this blue graph right here, it's kind of hard to see, but the slope of this blue graph would actually be 1 meter per second. Okay, and if I had all of the numbers on there, I could actually calculate the slope of that line. Now, what happens if you have a negative velocity? Well, we've talked about before, if you have a negative velocity, that just means you're moving in the negative direction. So now I'm going to give the moving man a velocity of negative 2 meters per second. And so that means when I hit play, he's going to move back towards his starting position, and so we know the graph is going to go back down, but it should actually have a slope of negative 2. Okay, and so you'll see it's going to go down, and it's going to be steeper than this blue line right here. So let's see that. Okay, and so here we can see the moving man is moving backwards. The slope in this section of the graph is negative 2 because that's his velocity. Okay, and of course if he keeps going, he's going to move in the negative direction, like you can see. Okay, so position time graph, the two key pieces of information are that the y-intercept represents the starting position, and the slope on a position time graph tells you the velocity. Okay, because velocity is the rate of change of position. Okay, so let's do two quick examples. Example 1. Use the position time graph shown to the right to completely describe the motion of this object between 0 and 10 seconds. So here we have a position time graph. Okay, now the first thing I'm looking at on a position time graph is of course the starting position. So here the y-intercept, the starting position, is 0. Okay, so I would say this object starts with a position of 0 meters and travels with a constant velocity. Now we'll get into this in a minute. How do I know it's a constant velocity? Because if you look at the slope of this first segment right here, notice that the slope is not changing because it's a straight line. So this is a constant slope. And since the slope on a position time graph represents a velocity, a constant slope here also represents a constant velocity. Now, how do I know what the velocity is? Well, I need to calculate the slope. So the way you find slope is you basically do rise over run. And hopefully you remember this from algebra, but you can either do rise over run or you can use the slope equation. Either way is fine. So what I'm going to do is I'm going to go up 5 over 1. And so the slope here would be equal to 5 over 1, which is 5. That means the velocity of the object right here is going to be 5 meters per second. Now notice it doesn't have the slope the entire time because once it gets to here, the slope actually drops down to 0. His position here is not changing anymore, and so he actually stops moving. And so to answer this question, what I would say is the object starts with a position of 0 meters and travels with a constant velocity of 5 meters per second for the first 5 seconds before coming to a stop for the last 5 seconds. Okay, so from 5 seconds to 10 seconds, their position's not changing. That means they're not moving. Okay, so that's how you'd answer this type of question. Okay, pause there if you need to look at that. So let's take a look at another position time graph question. Okay, example 2. It says, the first part says describe this object's motion. I'm not going to type this out just to save on space, but here we have another position time graph. Now you might ask, how do I know this is a position time graph? Because I look up here, I see time on the x-axis, and this x represents position. I said that before. If it's a velocity time graph, you'll see a v, or velocity, up here on the y-axis. Okay, so this is an xt graph, which is a position time graph. So the first thing I'm looking at is where does the object start? Well, the initial position of the object, the y-intercept, is actually down here at -6. Okay, so I'm not going to type this out to save on space, but you would say the initial position of the object is at -6 meters. Then the object moves forward. Okay, notice his position is increasing at a constant velocity. And I know this is a constant velocity right here because this is a straight line. It's a constant slope. Now, if I want to find the velocity from t equals 0 seconds to t equals 4 seconds, basically what that means, t equals 0 seconds is down here, t equals 4 seconds is right here at 4 seconds, and so this first question, or the second question, is asking me for the velocity basically during this first segment. Now, how do you find velocity on a position time graph? Well, you look at the slope. We talked about that a few minutes ago. The slope on a position time graph represents the velocity. So I could do rise over run. I'm going to do this one slightly different just to show you there's different ways to find the slope of a line. But basically what I'm going to do is I'm going to pick 2 points on this graph. This point is, let's see, 0, -6. And this point right here is going to be 4, 6. And the equation for slope, or one equation for slope that you might have seen before, is y2 minus y1 divided by x2 minus x1. Some of you might be thinking, wait, I thought slope was rise over run. Well, that's basically what this is. Okay, the y2 minus y1 is the rise, because that's the up and down part, and the x2 minus x1 is the run, that's the side to side. Okay, so y2 is going to be my y value for my second point, so this is y2. This is going to be y1 because this is the y value for my first point. And then this is going to be x2, this 4 is going to be x2, and then x1 is going to be 0. And so I can use my slope equation right here to find the slope between these 2 points. Okay, so, and again, why do I want to do that? Because the slope on a position time graph represents velocity. So I have 6 minus -6 divided by 4 minus 0. 6 minus a -6 equals a positive 12. 4 minus 0 equals 4. And so that would be 3. And so the velocity of the object from 0 seconds to 4 seconds is going to be v equals 3 meters per second. Okay, and so that's how you would calculate the velocity from this position time graph. Now, what is the object's velocity from t equals 4 seconds to 8 seconds is basically asking me for the velocity of the second segment right in here. Okay, now I could use the exact same equation, but I don't actually have to do that because I know from algebra that if I have a flat horizontal line, that has a slope of 0, right? Because slope is rise over run, and this line segment right here is flat, so it has no rise. And so I know right away that the velocity is going to be 0 meters per second because the slope from 4 seconds to 8 seconds right in here is 0. Now you can also think of that as the y-axis represents position, and if your position is not changing, that's the same thing as saying that you're not moving. Okay, so the velocity equals 0 meters per second. And for the last question, what is the object's velocity from 8 seconds to 8 seconds to 20 seconds? 8 seconds is right here. 20 seconds is down here. And so it's basically asking me about this third segment of the graph right in here. And so I'm going to actually erase what's on the screen right now just so I have a little bit more space. So pause it here if you need to look at that. So I want to find the slope between these 2 points. And so I'm going to use the slope equation again. I'm going to write out these 2 points. This is going to be 8, 6. And this point down here is going to be 20, -6. Slope is rise over run. Okay, so slope is y2 minus y1 over x2 minus x1. Change in y divided by change in x. Okay, and so this is going to be my y2. This is going to be my y1. This is my y2 because, again, it's the y value of my second point. And this is y1 because it's the y value of my first point. Okay, and this 8 is going to be x1, and this 20 is going to be x2. Remember, when you write an ordered pair, it's always x, y. So I'm just going to find the slope between these 2 points. y2 minus y1, that's going to be -6 minus 6 divided by x2 minus x1, which is 20 minus 8. The -6 minus 6 is -12. 20 minus 8 is a positive 12. And so that's going to be a slope of 1. And so the velocity is going to be -1 meter per second. So in other words, this object starts off moving forwards, it stops for a few seconds, and then it moves backwards with a constant velocity of -1 meters per second. Okay, so that is the answer to the last part of that question. Okay, so pause it there if you need to take a look at that. Okay, so now we're going to look at velocity time graphs. And a velocity time graph basically shows you how the velocity of an object changes over time. Now, remember there's two main types of motion that we're dealing with in this unit: constant velocity and constant acceleration. So if you have an object moving at a constant velocity, let's take a look at what that would look like. Okay, so I'm going to reset this, and let's say my moving man is moving with a constant velocity of 1 meter per second. Now, I already know what my position time graph is going to look like, but now let's take a look at what my velocity time graph is going to look like. So this red graph down at the bottom is going to show you how velocity changes over time. If I have a constant velocity, I would expect a graph that is not changing. Okay, so let's see. And there we go. Okay, so notice my position time graph, my position is increasing. The slope of this graph would be 1 meter per second. This velocity time graph just has a constant value of 1. And so you can see the velocity is not changing. Okay, and let me change the value, make it a little bit faster so it's easier to see. I'm going to give it a constant velocity of 5 meters per second. And we can see how these two graphs are different. Okay, so these two graphs basically represent the same motion, but this is a position time graph and this is a velocity time graph. And here on the velocity time graph at the bottom, we can see that a constant velocity is represented by a horizontal unchanging line. Okay, so let's do another example. Example 3. Explain in a complete sentence how the car is moving based on its velocity time graph shown to the right. So it's very, very important that you always understand what type of graph you're looking at. So the first thing you should do in doing a motion graph problem is to know what graph am I looking at. Is this a position time graph or is this a velocity time graph? Because if this was a position time graph, if it's horizontal, that means the object's not moving. Okay, but this is not a position time graph. This is actually a velocity time graph. So I would say that this object is moving with a constant velocity. How do I know it's a constant velocity? Well, because the velocity is not changing. You can see it's like 10, 10, 10, 10, 10, 10. So it's moving with a constant velocity of 10 meters per second for 5 seconds, because the graph goes from 0 seconds to 5 seconds. Okay, so very simple constant velocity velocity time graph problem. Okay, so let's we're actually going to skip example 4 just for now, just to save time. I do want to point something out to you. Okay, so we saw what these graphs look like for constant velocity. If you have a constant velocity, your position time graph is going to be linear, and your velocity time graph is going to be horizontal. Okay, remember there's two main types of motion though. There's constant velocity and then there's constant acceleration. And what I want to show you right now, and you can see on this slide right here, but what I want to show you with the simulation is that when you add acceleration, the shape of the graphs change. Okay, so now I'm going to add an acceleration of 2 meters per second squared, and I want you to see how the position time graph and the velocity time graph change their shape. Okay, so watch this. Remember, if you have acceleration, then by definition, your velocity has to be changing. That's the definition of acceleration. Okay, so here we can see my velocity is actually increasing. He's moving faster and faster and faster. In fact, his velocity is increasing by 2 meters per second, because I gave him an acceleration of 2 meters per second squared. If you look at the position time graph, it's kind of hard to make out what the shape is, but it's no longer a line. And I will tell you what the shape is. It's actually a parabola. Okay, we're not going to get into why it's a parabola exactly. But you should be able to recognize based off of the position time graph whether the object is accelerating or not. Basically, if it's moving at a constant velocity, the position time graph is going to be a line. If there's any type of acceleration, the position time graph is going to be curved. So here, I'm going to give it an acceleration of negative 3 meters per second squared, and we'll see how the two graphs change again. So here we can see the velocity time graph. The velocity is decreasing, and the position time graph, we can see the curve. We can see this is now a downward parabola, but it's still a parabola. Okay, if you want to know why is there a spike right here, that's because the guy hit the wall, and when he hit the wall, he stopped, so his velocity shot down to 0, and his position is now no longer changing because he hit the wall and he's not moving anymore. Okay, so make sure you understand and are able to recognize the difference between constant velocity and constant acceleration when you're looking at a motion graph. Now, just to summarize all of the important things you need to know about motion graphs, take a look at this slide. Okay, on a position time graph, if you have constant acceleration, the shape is going to be a parabola. That's what parabolic means. It means the shape of a parabola. The y-intercept represents the starting position, and you can't find the slope on a position time graph if it's a parabola, because you guys don't know how to find the slope of a parabola. That's fine. A velocity time graph, the shape is going to be linear if you have constant acceleration. The y-intercept represents the initial velocity or the beginning velocity of the object, and this bottom one is the most important. On a velocity time graph, the slope represents the acceleration of the object. Okay, on a velocity time graph, the slope represents the acceleration of the object. On a position time graph, the slope represents the velocity of the object. Okay, remember, slope is rate of change. The rate of change of position is velocity. The rate of change of velocity is acceleration. That's like the definition of what acceleration is. So when you're looking at a velocity time graph, the slope of a velocity time graph represents the acceleration of the object. Okay, so just really quickly, let's take a look at example 5. What type of graph is this? First thing you should always ask, what type of graph is this? This is a velocity versus time graph. There's velocity, there's time. The question says calculate the acceleration of this object from 0 seconds to 3 seconds, from 3 seconds to 5 seconds, and from 5 seconds to 8 seconds. So basically, this segment, and then this segment. Now, remember, on a velocity time graph, the acceleration is represented by the slope of the graph. So if I want to find the acceleration, I need to find the slope. Okay, now this is actually very easy because if you look at this first part here, the velocity is not changing. In fact, the velocity is 0, so the object's not even moving here. Okay, what is the slope of a horizontal line? Okay, that would be 0. So from 0 seconds to 3 seconds, I can tell you right away that the acceleration is 0 meters per second squared because the object is not changing its velocity. In fact, the velocity is 0, and so the slope of this line segment right here is not changing. The slope is 0. From 3 seconds to 5 seconds, the way I'm going to find the slope, again, is I'm going to pick 2 points on the graph. Okay, so this is going to be 3, 0, and this is going to be 5, 8. I always pick the endpoints just to make it easier to find the slope. Okay, I use my y2 minus y1 divided by x2 minus x1 equation, my slope equation. Slope is rise over run. I plug into my equation. Okay, so that's going to be 8 minus 0 divided by 5 minus 3. That's 8 over 2, which is 4. So from 3 seconds to 5 seconds, the acceleration is 4 meters per second squared. Okay, so right from here to here, the object is accelerating. Its velocity is increasing by 4 meters per second each second. And then from 5 seconds to 8 seconds, we can see right in here, the velocity is constant. The object is no longer accelerating. And so the slope of a flat line segment is 0. And so it's 0 meters per second squared again. And the last question just says, during what time period is this object moving forwards? To move forwards means your velocity has to be positive. So it's basically asking, when is the velocity positive? Well, if you look at this graph, the velocity is always positive. And so you would basically just say, always. Okay, don't get confused here. The velocity is decreasing here, but even though it's going down, the velocity is still a positive value. It's just getting smaller. Okay, but the velocity itself is still positive. So it's always moving forwards. Okay, so that's basically it for motion graphs. We can take a look at one more quick example. Pause it here if you need to. Example 6 basically just says, during which segment is this object moving at a constant velocity? First things first, what type of graph am I looking at? Velocity time graph. On a velocity time graph, what does constant velocity look like? Well, it looks like the velocity is not changing. Okay, so which line segment shows the velocity with a constant value? That would be segment B. Okay, and then during what segment is this object moving at a constant acceleration? Constant acceleration means the velocity is changing. Okay, so during what segment is the velocity changing? Well, that would be segment A and C, because during both of these segments the velocity is increasing. Okay, now we're not going to do the last calculation just in the interest of time, but you're welcome to try that on your own. Please let me know if you have any questions, and as always, I will see you guys in the next video.